last lesson, we looked at how to simplify rational expressions. We talked about how rational expressions are just like fractions. And we also stated how we didn't want any of our denominators to equal 0, so we needed restrictions. In the lesson today, we're going to look at how to actually operate with different rational expressions, such as multiplying, dividing, and adding and subtracting. But before we get there, let's take a look at some numerical examples before we put in some rational expressions. So we're going to remember how to multiply fractions. We have here 1/3 multiplied by 2/5. Remember, when multiplying by fractions, we simply multiply the numerators together and multiply the denominators together. So 1 times 2 is 2, and 3 times 5 is 15. If we have bigger numbers, like 12/15 times 5/9, it might even make sense to reduce the fractions first before multiplying across. So any numerator can reduce with any denominator as long as everything is multiplying and dividing. You can even reduce from one fraction with another fraction. So this 12 and 9 can both reduce by dividing by 3. So this would become a 4, and this would become a 3. This numerator 5 and this denominator 15, those can reduce as well, becoming 1 and 3. And now since everything's been reduced fully, we can multiply across. So 4 times 1 is 4, and 3 times 3 is 9. Multiplying rational expressions will work in a similar way. We're first going to factor all of the numerators and denominators as much as we can. Then we'll cancel and reduce anything that we see in common. We'll then multiply the numerators and multiply the denominators, and then reduce. The only difference is we'll now also need to check for any restrictions. So what are values of our variable that will cause our denominator to equal 0? Here's a really simple example to start. Multiply x over 2 times x over 3. There isn't anything we have to factor here, so we can just multiply the numerators and the denominators. X times x is x squared, and 2 times 3 is 6. So we end up with x squared over 6. But let's get a little bit more complicated here. Let's say we have 2a cubed divided by 5b cubed times c, then multiplied by 3bc cubed, all divided by 8a cubed. Here we're going to want to reduce first. In order to reduce, we want to look at the coefficients that are in front of the variables. So we have a 2, a 3, a 5, and an 8. Remember, any number that's in a numerator can reduce with any number in a denominator as long as everything is multiplying and dividing. So the 2 that's in front here, it can reduce with the 8 that's in the denominator there. And both of them can be divided by 2, so we're left with 1 and 4. The 3 and the 5 can't be reduced further, so there's nothing more we can reduce. Let's look at the variables. Any variable that's in a numerator can still reduce with any variable that's in the denominator using exponent rules. So if we have a cubed in this numerator and a cubed in this denominator, those will fully cancel. So this a cubed and this a cubed can just be scratched out. 1b that's in this numerator and 3b's, or b cubed, in this denominator, while using exponent rules, this 1b will cancel with one of the b's down here, leaving us with b squared. And the same rule would apply with the c's. This c will cancel with one of these c's, and we'll be left with c squared. It's a little confusing to look at after all that reducing, but if we pay close enough attention, we can read across the numerator and see that we're left with a 1 multiplied by 3c squared, which is just 3c squared. And 5b squared multiplied by this 4 that's still there, well, that will multiply. 5 times 4 is 20, and the b squared is the only part of the variable that's still left. So our final answer is 3c squared over 20b squared. Don't forget the last step here, where we need to figure out what the restrictions are. What are values of any of the variables that would have caused any denominator in the question to equal 0? We can't just look at our final answer. We need to look prior to our final answer before we started canceling and reducing. Notice in our original fractions, we had variables of b cubed and c, and a cubed as well. And everything's multiplying with each other. So if any of those variables equals 0, the entire denominator would equal 0. That's going to force us to say that none of these letters, A, B, or C, could equal 0, as it would cause those denominators to equal 0. So far, so good. But now we're going to look at more examples where factoring is going to come into play. Remember, the common mistake that students often make is they decide to reduce or cancel prior to factoring. And this isn't mathematically possible, as all of these numerators and denominators have to add or subtract with each other prior to being able to cancel with anything in a numerator or denominator. So we need to factor these things fully first. Look at each numerator and each denominator for each fraction and see if you can factor them. Try this on your own first, and then hit play again to see the solution. We'll start with the first numerator. 3x plus 6, you can take a common factor out of 3. So you're left with x plus 2. In the denominator, 7x minus 7, again, we can take out a common denominator of 7, and we're left with x minus 1. We'll now multiply to the other fraction. 14x minus 14, we can take out a common factor of 14, and we're left with x minus 1. And 5x plus 10, common factor at the 5, and we're left with x plus 2. Now we have both fractions with two factors in each numerator and denominator. All of those things are multiplying and dividing. So if you see anything that's exactly the same on a numerator and a denominator, it can cancel out. So this x plus 2, it can cancel out with the x plus 2 down here. And this x minus 1, it can cancel out with the x minus 1 down there. They're exactly the same, so that's why we can cancel. Look at the coefficients now. Is there anything that can reduce? Absolutely. This 7 and this 14 can reduce to a 1 and a 2. The 3 and the 5 can't really be touched further, so now we can multiply. 3 times 2 is 6, 1 times 5 is 5. And our final answer reduces to 6/5. It's funny how all of this that was up here to start with reduced all the way down to 6/5. We can't forget our restrictions, and it looks like there shouldn't be because there's no variables in our final answer, but we have to do our restrictions based on what was there prior to us canceling. So look at the denominators prior to canceling. We have a 7 bracket x minus 1, and we have a 5 bracket x plus 2. By observation, we can see that x would have to equal 1 for this bracket in order for that to equal 0. So we want to restrict that. And we also want to restrict negative 2, as it would force this bracket to equal 0. So our two restrictions are positive 1 and negative 2. Moving on to example 4, we come across a little bit of a roadblock. We have two fractions now that are dividing with each other rather than multiplying. We've learned in the past that in order to divide fractions, we want to flip and multiply. Or, I guess mathematically speaking, we're going to take the reciprocal of the second fraction and change it into a multiply question. So let's do that. We're going to have x squared minus 3x plus 2 all over x squared plus 3x plus 2. And we're going to now flip or take the reciprocal of the second fraction, and it will change it into a multiply question. So the 8x minus 8 will now go into the numerator, and the 4x minus 8 will go into the denominator. I'm going to put a little star off to the side here because we're going to have to come back and remember that we made this little reciprocal action, or this flip. But let's carry on. We now have to factor all of these numerators and denominators. We have some simple trinomials here where we'll use some product method, and some of them will just use common factoring. So hit pause, try this out, reduce it as much as you can, and get to your final answer. And then come back and check to see if you did it right. Starting with the first numerator, a simple trinomial where we need two numbers to multiply to 2 and add to negative 3. Well, those two numbers are negative 1 and negative 2. For our denominator, x squared plus 3x plus 2, same sort of idea, 1 and 2, but now they're going to be both positive. we're going to multiply to 8x minus 8. We're going to take a common factor out of 8, x minus 1. And for x minus 8, we'll take a common factor out of 4, and we're left with x minus 2. Now everything's multiplying and dividing. So is there anything that is common or that we can reduce in the numerator and denominator? Well, this x minus 2 can cancel with this x minus 2. It's in a numerator and denominator. This x minus 1 cannot reduce or cancel with this x minus 1. They're both in numerators, so don't even think about canceling them out. The 8 and the 4, though, can reduce. This 8 and 4 will reduce to 2 and 1. That's about it. Nothing else is exactly the same. And don't just cancel an x with an x. They're in brackets with other operations, so we can't just do that. So what are we left with? We're left with a 2 and 2 x minus 1 brackets in the numerator. So to write that, we're going to write our 2 out first. It's the coefficient. And then we have an x minus 1 and another x minus 1. So we'll just call that x minus 1 squared. In the denominator, we don't have a coefficient anymore. It got reduced to 1. But we do have an x plus 1 and an x plus 2. So we're going to write those brackets as separate brackets here. X plus 1 and x plus 2. This is in fact as simplified as this gets. And you're going to see that we're not going to re-expand in the denominator and the numerator. We're going to keep them factored. It's a nice and neat way to keep it rather than expanding it all back out again. But we do need to state our restrictions. So let's go back into the question prior to us canceling or reducing any of the brackets. I'm going to underline all of the different brackets here that we have to look at. The x plus 1, the x plus 2, and this x minus 2 that's right there. By observation, we can see that our restrictions for those three things are going to be that x can't equal positive 2 right here, negative 2 right here, and negative 1 right here. So what's that? Negative 1 and positive and negative 2. But there is this one other spot we have to look at, and I start it for a reason. Remember, we flipped our numerator and denominator of our second fraction in the opening line of our solution. Well, this 8x minus 8 that is currently in the numerator right here used to be in the denominator, right? It was in the denominator right here. Well, that denominator can't equal 0 either. So we have to restrict on that spot as well, right here. Well, what's the restriction that would make that bracket equal 0? Well, the restriction is that x can't equal positive 1. So that's a fourth restriction that we have to consider. And it's one that's often missed. When we divide rational expressions, not only do we have to consider the denominators of both of our fractions, but also the numerator of the second fraction, as it used to be a denominator prior to us taking the reciprocal. Now that we know how to multiply and divide rational expressions, we're going to take a look at adding and subtracting rational expressions. If you can remember way back to primary school, when you first learned about adding and subtracting, it was so easy. 2 plus 3 equals 5. 4 minus 1 equals 3. How hard is that? When we got to multiplying and dividing, things got a little bit more complicated. Well, now that you're in grade 11, and we're learning how to multiply, divide, add, and subtract rational expressions, the opposite kind of thinking is needed. Multiplying and dividing rational expressions is easy. Adding and subtracting rational expressions, these are a bit more complicated, and they take more steps and more care to solve. But before we add and subtract rational expressions, let's take a look back at how we add or subtract fractions without variables in them. Our example we're going to look at is 1/12 plus 1/20. How would we approach doing this question? Well, we'd want to find a common denominator. So in your head, you would try to figure out, well, what is the lowest common multiple of 12 and 20? And you're going to go through a few numbers in your head, and eventually you'll come out with the answer being 60. 60 is our lowest common multiple. But how did your brain do that? How did you figure out that 60 was the lowest common multiple? Well, I'm going to show you what your brain is processing and how it came up with 60 as the answer. Let's start with the number 12. It's one of our denominators. What are two numbers that are factors of 12? We hear this word factor all the time. Remember, factor just means two numbers that will multiply into 12. Well, you could think of two numbers like 3 and 4. 3 is a prime number. We call this a prime factor because it can't be reduced any further. But the number 4 can. 4 isn't a prime number. It's a number that we can find more factors. In fact, the two numbers that multiply to 4 are 2 and 2. These 2's are prime numbers, or we can call them prime factors. So I'm going to put little boxes around them as well. And we can write out the fact that 12 is just equal to 2 times 2 times 3. 2, 2, and 3 are the prime factors of 12. Let's do the same thing for 20. If you find two numbers that multiply to 20, let's say 2 and 10, well, 2 is a prime factor. So we're going to put a box around there. 10, we can find two numbers that multiply to 10, say 2 and 5. And again, 2 and 5 are prime factors. So let's put boxes around those too. So 2 multiplied by 2 multiplied by 5, that equals 20. And it turns out that those are the prime factors. 2 times 2 times 5 equals 20, and 2 times 2 times 3 equals 12. All right, what are you getting at? Well, in order to figure out the lowest common multiple, what we want to do is realize what factors do these two numbers have in common. Looking at the factors of these numbers, we see that both 12 and 20 have two factors of 2. This is common to both of them. So I'm going to take those two factors of 2 and set them off to the side. I also notice that 12 has a factor of 3. It's not common with 20, so I'm going to take that factor of 3 and set it off to the side as well. Same thing with this factor of 5. 20 has it, but 12 doesn't. So I'm going to include it in our group. So our group right now has two factors of 2 because it was in common, a 3, which was only the 12 had, and a 5, which only the 20 had. And what we're left with here is what our common denominator is. 2 times 2 times 3 times 5. 2 times 2 times 3 times 5 is 60. And that's what we figured our common denominator was. And our brain did all this work without us realizing it. But the concept of what we did here is what's going to be important when we want to add and subtract rational expressions. Notice how we factored or found the prime factors of these numbers. We need to find the prime factors or the factors of our rational expressions. Then we're going to see what they have in common and keep that in our common denominator. And then anything they have different, we're also going to include that in our common denominator. So here's our first example. 5 over 2a plus 1 over 3a. We're going to look at our denominators first. What do they have in common? Well, in common they have an a. They both have an a. So our common denominator is going to include an a. What they don't have in common is a 2 and a 3. So we're going to need to include a 2 and a 3 in our common denominator. Well, 2 times 3 is 6. So if we include both, it would actually turn into 6a. And that makes sense to us. 6 is the lowest common multiple between 2 and 3, and they both have an a. So to figure out our numerators, we now want to ask ourselves, what did we multiply to this first fraction so the denominator turned from 2a all the way to 6a? Well, 2 times 3 equals 6a. So we're going to have to do that same move to the numerator. 5 times 3 needs to be what our new numerator is, and that's 15. For our second fraction, how did we get from 3a to 6a? Well, from 3a to 6a, we multiply by 2. So our numerator on that second fraction has to be the same operation. 1 times 2 equals 2. And now we'll add these fractions together. It's different than multiplying. We don't multiply the numerators and multiply the denominators. So we wouldn't add the numerators and add the denominators. We just simply add the numerators and keep the common denominator the same. 15 plus 2 is 17. 6a is our remaining denominator. So our final answer is 17 over 6a. We can't forget to mention the restrictions. So our restriction here is that a can't equal 0. And we can see that if a was 0, our denominators would equal 0. Here's one that's a bit more complex. 5 over 8x subtract 7 over 12x squared. The fact that we have an addition sign or a subtraction sign won't change the process. It may just make things a little bit trickier with the subtract sign, but we'll get to that. Our common denominator here, let's start with the coefficients. 8 and 12. Our lowest common multiple between 8 and 12 is 24. So 24 is going to be the coefficient in our common denominator. X and x squared are now the two variables we have to consider. The nice rule of thumb here is always pick the version that has the highest exponent on it. So if you have an x and an x squared, your common denominator will be x squared. It doesn't need to be x cubed. X squared is sufficient enough. It's the lowest common multiple. But always pick what the highest exponent is. Alright, so now we'll ask ourselves, how did we get from 8x all the way to 24x squared? What did we multiply by? Well, 8 times 3 got us to 24, and x times x got us to x squared. So we have to do the same move to our numerator. 5 times 3x is 15x. For the 7, we're going to need to figure out how 12x squared became 24x squared. That is just multiplying by 2. So 7 multiplied by 2, well, that equals 14. Our final answer here, when we add or subtract the numerators, these are not like terms, so 15x minus 14 is our numerator, and our denominator is this 24x squared. Looking at the restrictions, again, we don't have any addition or subtraction in the denominators, but we can see that our only restriction will be that x can't equal 0. Here's an example where the subtraction will come into play. We have x plus 2 over x minus 1. Subtract 2x minus 3 over x minus 1. Our denominators are already common, so this is going to be pretty easy to write out as our common denominator, x minus 1. But where we have to be careful is the subtract sign in between. We're going to take our numerator x plus 2. It won't change because we didn't change the denominators. But now we're going to subtract 2x minus 3. The common mistake here is to subtract the 2x and then say minus 3. But this subtract sign doesn't just apply to the 2x. It applies to this entire numerator, the 2x and the minus 3. So we're going to want to adjust this by saying we're going to subtract not just the 2x, but that entire bracket, minus 2x subtract 3 in brackets. When that simplifies, we'll have an x plus 2 minus 2x plus 3, because we have a subtracting a negative there, over x minus 1. And then clearing up the numerator, x minus 2x is negative x, 2 plus 3 is 5. So we have negative x plus 5 all over x minus 1. If you got this question on an assignment, you may even see the answer written as 5 subtract x rather than negative x plus 5. It just looks a bit cleaner when you don't have that negative sign sitting out front. Our restriction here is that x can't equal 1. Hopefully that's obvious to see. Alright, the final example we're going to see in this lesson. We have two denominators where they are both trinomials, a squared minus 5a minus 6 and a squared plus 3a plus 2. Hopefully your gut instinct here is you would want to factor these. So let's factor both of these denominators and see what we end up with. A squared minus 5a minus 6 is a simple trinomial. So we're going to factor using sum product rule. two numbers that multiply to negative 6 and add to negative 5 are negative 6 and positive 1. Subtract, and to factor the denominator on the second fraction, a squared plus 3a plus 2, two numbers that multiply to 2 and add to 3. Well, that's easy. A plus 2 and a plus 1. Now we have to find a common denominator. Let's look at our factors. Both fractions have a factor of a plus 1. That is common between them. So for our common denominator, we're going to want to include a plus 1 as one of the factors. Now what do they have that's not in common? There's an a minus 6 in this fraction and an a plus 2 in this fraction. We need to include both of those in our common denominator. So an a minus 6 and an a plus 2. Notice how even though we have two brackets that are a plus 1, we only wrote 1 in our common denominator because both fractions had that in common. We only need to write it once. Alright, our first fraction had factors of a minus 6 and a plus 1, but our common denominator also includes a factor of a plus 2. That's different in our first fraction. So what we multiplied to the numerator is the factor or factors that are new to the fraction. And in this case, the a plus 2 is new. So we're going to take our numerator of a and multiply it by a plus 2. It's the new thing. The numerator on the second fraction is a 2, but don't forget the subtract sign. We're going to put a subtract sign 2. And the factor that's new to this fraction, it already has an a plus 2 and an a plus 1, is the a minus 6. So we're going to multiply this numerator by a minus 6. When working through this problem, our common denominator of these three factors will just remain the same. You're going to have to just write these factors out every single time. Sometimes I like to just write them in numerical order here. So a plus 1, a plus 2, and a minus 6. And now we'll expand and simplify the numerator. A times a is a squared. A times 2 is 2a, negative 2 times a is negative 2a, and negative 2 times negative 6 is positive 12. Where we end up here is we will want to finally simplify this numerator. So the two a's will cancel each other out, and we're left with a squared plus 12 in the numerator. And the denominator has all three of these factors, a plus 1, a plus 2, and a minus 6. Again, we don't want to expand this out, just leave them factored. It's nice. So this question has now been fully simplified. The a squared plus 12 can't be reduced any further. They're not like terms, and we have our three factors in the denominator. The last step now is to state the restrictions. So before we canceled anything, and we haven't canceled anything, so just look at your common denominator. The three values that a cannot equal by observation are negative 1, negative 2, and positive 6. And now you're done. Operating with rational expressions is not that hard, but you do need to make sure you follow all the appropriate steps. Factoring is essential for this unit, so please ensure that you know how to factor properly. Not only simple trinomials, but you'll see complex trinomials or difference of squares or perfect square trinomials as well. Be comfortable with factoring and be comfortable with knowing how to properly reduce and simplify fractions. If you have all that figured out, then you're going to do just fine.